The broadcast is now starting. All attendees are in listen-only mode.
Hello, good morning everyone. So we'll be starting today's webinar session. Let's do a quick sound check before that. So kindly raise your hand if you are able to hear me clearly and you are able to see the screen as well. Okay, I see few hands. I would request others as well to kindly raise their hand in the chat window so that we can start the webinar as soon as possible. Okay, I see many hands here. So I hope everyone can hear me and are able to see the screen. So if you are facing any issues, like if you can't hear me or you can't see the screen, kindly raise your hand or else we are going to start now. Okay, so we are going to start now. So good morning everyone. Welcome to this ongoing webinar series by Midas Civil. I am Anuj Asati. I am working at Midas R&D Center in India in Navi Mumbai. So, topic for today's presentation is real structure interaction analysis. So, we'll be starting that now. So, before that, so if you have any questions related to the topic, kindly ask them at the end of the webinar. So I'll try to answer as many questions as possible, but as there are large number of attendees, so if we miss any questions, we'll make a questionnaire and we'll answer all the questions and mail it to them, mail it to you. Okay. So yeah, so let's begin the webinar for today. So topic for today is rail structure interaction analysis. So contents for today's presentation is first, I will give you a brief introduction about rail structure interaction analysis. What is rail structure interaction analysis? Why we need to do rail structure interaction analysis for our bridge. Then we will see an overview of how to do that in Midas Civil. So we have a dedicated wizard for that, which is called Rail Track Analysis Model Wizard. So we will look into deep how to use that wizard and how to generate model and generate report using rail track analysis model wizard. Then post that, if you have any questions, we'll have a discussion session, a brief discussion session at the end of this webinar. So let's begin in today's topic, which is rail structure interaction analysis. So first of all, why we these days why we need to do rail structure interaction analysis. So the first thing is because we are these days now railways are using continuous weld rails instead of brake rails as we were using earlier. So continuous weld rails or long weld rails are nothing but rails continuous more than 200 meters and they are connected via weld at distance more than 200 meters. So the necessity of continuous well rails is it reduces the impact forces on rails and increases the lifespan of rails, and it also increases the rider's comfort. It decreases the noise and vibration on the rail. So as you can see in this image here, earlier we used to go for rails of length around 25-30 meters, and they were used to connect it to each other via fish plate. But now these days these types of rails are not being used, so they are being continuous. We are going for continuous rails which are more than around up to 801 kilometer also. They may go up to 801 kilometer, and they have their welding joint at that around at the spacing of 800 meters. So as I already told you that it reduces the vibration losses and decreases the noise. It improves the rider's comfort, but it what it does is it there are various other challenges that come into picture due to use of these continuous weld rails. So just to give you an example, like when we were using this normal rails connected via fish plate, so we had this gap between rails. So whatever temperature stresses used to come in the rail, they used to get released at each 25 meters or whatever spacing we used to provide this fish plate. But now, when we are going for these types of continuous well rails, so uh, okay, see that some of you have raised a question that you are not able to hear me. Uh, is it like okay? Many of you are able to hear me. I think the people who are not able to hear me, the problem is at your end. I guess you need to check if all the things, if you had not muted yourself or something like that. Okay, so now in continuous well rails, what happens? The release of stress due to temperature rise and due to temperature fall. The release of stress is at 800 meters, or wherever I have provided expansion joint, or I have provided the connection between the rails. So due to this, along the length of the continuous rail, there is an accumulation of stress due to temperature. Just for example, just one load case which I am discussing here. So due to temperature, there is a accumulation of stress which is happening in the rail. So due to this, it may cause buckling of rail, fracture of rail, and as you may know, failure of rail may lead to a catastrophic accident, such as derailing of the train, or it may be very catastrophic and it may lead to a huge loss in life and property. So, so that is the reason why we need to go for this rail structure interaction. Basically, we need to check due to the use of continuous weld rails, uh, the additional stresses which are coming in my rail. Is my rail adequate enough to take those stresses? And the deformations which are going to happen in the rail, is my ballast and my support system adequate enough to take those serviceability, to sustain those serviceability criteria? Okay, so this is the basic idea of why we are going for a rail structure interaction analysis. Okay, so let's move on now. Now coming to the loading. So basically now there are three types of loading for which we need to do the rail structure interaction analysis. So I'll just tell you the loads and the reason why we need to do, I will just give you a brief of that. So the three loads for which we need to do rail structure interaction analysis is, first is traction braking loading, second is temperature loading, and third is train vertical load. So for temperature loading, as I told you earlier in the previous slide, that due to elongation and contraction of my, due to the rise and fall of temperature, as my rail is not able to expand or contract, there is accumulation of stresses in my rail. So this accumulation of stress may lead to fracture or may lead to buckling of my rail. So that is the reason why I need to check for temperature. Now coming to vertical load. So for vertical load, what happens is, now suppose we have the rails which are placed on the ground. So when the train is moving over the rail above the ground, so the transfer of load through the rail to the ground is through compression only. So like just for example, a beam is placed on a solid rigid ground and I have applied a load on that beam. So whatever force coming on the beam is transferred to the ground via compression. But in the same way, if I have placed that beam between two supports and I have applied a uniform distributed load on the beam, so now the transfer of load from to the supports is happening via bending of my beam. Now, if we imagine a third case where a simple uh, a, another beam is placed over the beam and this whole system is supported by two supports. Now, if I apply a UDL load, so the transfer of load from the rail to my deck slab and from deck slab to the support, it will be a combination of compression as well as bending of both rail and deck. So that is the reason why we need to do a interaction check between the rail and the deck for vertical loads as well. Now coming to traction and braking loads, so whenever there is a tractive force or braking force applied on the rail, so my rail will try to move with the direction of force. But as it is connected to my ballast, it is connected to the deck via ballast, the deck will try to stop that. So due to this, there will be an interaction happening between my rail and the deck, and stresses will be generating due to braking and traction effect in deck as well as in rail. So we need to check for all these three conditions for in rail structure interaction. So I hope this is clear. The reason why we are doing for all these three cases. Now moving on. Now the transfer of force. So basically, due to interaction effect, the predominant force which is coming in my rail due to the rail structure interaction is axial load only. So we can imagine it as a top reinforcement of beam. So in reinforcement, the forces are usually axial. So either compression or tension. So similarly, due to the interaction in my rails, the forces are predominantly compression or a tension. So now, how if you see this figure, so this figure basically shows how the force accumulation takes place due to thermal load. So as I told you, this is the total length of my this is the total length of my continuous weld rail, and at these locations, this location and this location, I have provided a expansion joint or a rail joint here. So what the 150 meters here, the release of stress will take place, but in this region, if you see the middle part of the region, here the stress remains constant due to variation of temperature. So basically, if my bridge is lying somewhere in between this location, so in this location the stresses will be constant in my rail. So I need due to temperature variation. So due to this axial force in the track on embankment, so this is for embankment, but in bridge what will happen, my deck not being permanently rigid, so interaction will happen and some other stresses will generate. Okay, so moving on. So now for doing rail structure interaction, so Indian code does not have any specific guidelines as such for rail structure interaction. So IRS code just gives a refers to UIC 774 part 3 for all the stress checks and for all the stress checks and the serviceability checks. Just what IRS code specifies is the strength. So here, like UIC guidelines tell us for concrete bed and for ballast bed, for tensile strength it specifies 92 Newton per mm square, and for compressive stress it specifies us for 72 Newton per mm square. But as per IRS guideline, these strengths has been revised, and for compressive stress, the strength is 60 60 Newton per mm square, and for tensile, it is 75 Newton per mm square. So basically, this is one difference, and the second difference, which is the IRS code specifies the stiffness of my ballast for loaded condition is 50 kilonewton per meter, and for unloaded condition it specifies as 25 kilonewton per meter square. So these are the two things which IRS code specifies us to check. Rest of for rest of the checks, it refers to UIC 774 Part 3 guidelines. So usually UIC guidelines are universally accepted guidelines for real structure interaction. So basically, we also will be doing it as per UIC 774. Okay, so yeah, so this was for stresses. Similarly, for longitudinal relative displacement in bridge deck, due to traction and braking load, the maximum displacement allowed is 5 mm, and due to longitudinal displacement, basically the rotation of deck, the maximum displacement allowed is 8 mm. So what is this 8 mm? Let me just show you. So basically, due to this rotation of my deck, so there will be a displacement happening in my at the top of my deck. So the as per UIC guideline, this displacement should be less than 8 mm. And coming to the other thing, due to relative displacement between deck and rail, it should be less than 5 mm. Okay, so these are the few things which we need to check. So now just to sum it up, so we are doing RSI analysis basically to find the additional stresses coming in my rail due to braking, vertical and traction loading and temperature loading. And another thing which I need to ensure is the serviceability condition of my deck. So basically, the longitudinal relative displacement in deck should not be greater than 5 mm, and the longitudinal deck rotation displacement due to deck rotation should not be greater than 8 mm. So the reason for doing this serviceability check is because most of the bridges, my rails are placed on the deck wire and connect. There is ballast. We are the connection between rail and the deck. We are doing it as with ballast. So usually, if you see, most of the rail bridges will have ballast in them. However, in metro projects coming these days, they have a concrete bed. So when in specifically talking about the ballast bridges, so if these serviceability conditions are breached, so basically the stability of my ballast is compromised. So to ensure the stability of the ballast, we need to satisfy these serviceability criteria. So if the stability of my ballast is breached, basically the connection between my rail and deck is somewhat it's disturbed. So I need to ensure, one is the limit state of strength of my rail as well as the serviceability criteria also I need to take care. So these are the two things which we are checking. First is the stress in rail. Second is the serviceability criteria between deck and rail. Moving on. Now coming to loading. So basically, for temperature loads, the UIC specifies for deck, it specifies 35 degree temperature variation plus minus, and for rail it specifies for around 50 degrees centigrade. Okay, but there is one more clause in this in UIC code. If you have your bridge placed in this non-expansion zone. So basically in this non-expansion zone, there is no elongation or contraction happening in your rail. So basically if you apply this load on the rail, so basically your rail is not going to expand or contract. So basically it is not going to affect the stresses, the interaction stresses of your rail or deck. So basically if your bridge is coming in this your non-expansion zone. So in that case, we don't need to apply temperature load on our rail. So we need to apply only on our decks. Now for traction and braking, so I'll be doing this as per IRS code guidelines. So like this loading we can get from as per whatever analysis if you're doing for metro bridge or if you're doing for a railway bridge. So it depends on what type of project you are handling, and based on that we arrive at this traction braking and vertical loading. So what I will be taking I will be referring to DFC loading as I will be doing it for a railway bridge. So 32.5 ton axle loading we will be referring to. And another thing, if you see in DFC, if you see refer to IRS code guidelines, they give a equivalent uniform distributed load. If you see in Appendix 26, they have provided equivalent EUDL loadings. So I'll be referring to that. So how I am going to calculate the EUDL load is by I'll be doing it based on my span. So suppose if I'm considering 30-meter span, so based on that I will interpolate the values for my vertical braking and traction loading. Moving on. Yeah. So before we come to this slide, let me give you. I will come back to that slide. First, I need to tell you something about the ballast first. Yeah. So basically, one thing is. As you might be knowing that rail structure interaction is not a linear analysis, it is a non-linear analysis. So what I mean by non-linear analysis is basically the ballast stiffness is not constant as it's not constant throughout the train running it from one end to another end. So basically this ballast stiffness changes if it is loaded or it is unloaded condition. So it can be like easily imagined. Imagine a book kept on a table, and if you try to move that book, you can easily move it. But if you keep a very heavy load on that book, and now if you try to move, it will be difficult to be moved. So, if we try to draw an analogy, so here if my rails are loaded, so there the stiffness increases to 50 kilonewton per meter square, and if this if it is unloaded, the stiffness is 25 kilonewton per meter square. So this is the main reason why it is a non-linear analysis, and why we cannot do a simple moving load analysis as we do for normal highway bridge. We can't do like that in for our rail structure interaction. The main reason being, if my train is moving, so wherever my train is placed, at those locations, the stiffness of my ballast will be as per the loaded condition, which is 50 kilonewton per meter square, and the rest of the bridge will have a stiffness of 25 kilonewton per meter square. So due to this reason, we don't. So now my analysis being non-linear, so I cannot combine my stress as linear superimposition as shown here. So as the non-linear analysis, I cannot superimpose the results from the non-linear analysis linearly. I cannot superimpose them. So this type of approach should not be done ideally. But what UIC specifies is we can go for this approach. So basically what happens when I linearly superimpose the results, the variation in result is around 10 to 30% depending on the type of bridge. but it is always on the conservative side. So there are two types of analysis. So here there are two ways to do real structure interaction analysis now. So one is the simple approach, like I separately do my thermal load analysis, I separately do traction braking load analysis, and I separately do vertical load analysis. And I superimpose the results whichever I am getting. So my results, whichever I will get here, will be on the conservative side, as that I will give you more in detail in a further slide. We will discuss more why it is on a conservative side. And if there is another way, is complete analysis. In that, in single model, I will apply all these three loads. So thermal load, tracking, braking load, and train load. All these three are applied in a single go, and the analysis is done. Okay, so moving on. Now there may be cases when the stresses in my rail will exceed, as mentioned in either my stresses will increase to the specified limits, or my serviceability criteria may fail. So in that cases, there are various ways to counter this issue. So we have done various case studies as well. So one is by changing the support condition layout. So basically what I suppose, so now suppose your bridge is a simple supported bridge. So your one abutment being fixed and your other abutment being free. So this is my normal support layout with fixed free kind of support. So what we can do, either we can change this supporting layout. So either I can change this my fixed abutment as a free abutment and my free abutment as a fixed abutment. So here I will get some change in stress and the serviceability criteria. Second, what I can do, I can make both of my abutments as fixed and my center pier as free. So that is also an approach. So depending on various support conditions, I can change different support conditions, and I can find out I can make my stresses pass. I can bring them back in limit. Second is span composition. So we will see this. I will show you a case study which we have done. So basically, by changing the span configuration, so keeping my largest span near the support, and by near the free or fixed support, I can change the stresses. And the third is stiffness of deck. So by changing the stiffness of deck, it very minutely changes the stresses. Basically, the idea behind this is the more the stiffness of deck, less will be the bending of my deck, less will be the bending of my rail, and less will be the forces generated in my rail. So this is also one approach to go for reducing the stresses in my rail. And if all these three approaches do not satisfy, then we try to go for zero longitudinal resistance rail fastener. So here in this case, sorry, the longitudinal resistance is made zero. So the arrangement is somewhat like this. So basically no resistance is provided at this location. So my rail is free to move here. So as my rail is free to move, whatever stresses are accumulated at this zone, these stresses will be released. So you can see here in the image, these are the location where free zero resistance, zero longitudinal resistance rail fasteners are provided. But these things have their own challenges. So economic efficiency is very less for this type of arrangement. So the maintenance cost will go up drastically for this. So usually we don't go for this type of arrangement. We usually try to bring our stresses in limit using these three mostly. Okay. So the same approach I have deduced as a flow chart, and I've explained it here how these things. So how if your stress is exceeding the limit, how by changing your support arrangement, then by changing span composition. So those things I have already explained you, and just Here we have shown it in a flow chart. Okay, so moving on. Now the computational model. So basically, the considerations which we are doing for our computational model is usually we are concerned with only the stresses in rail and the serviceability criteria between deck and tail. So for that, we usually go for a line model for my superstructure. So this specifically, whole model will be a line model. So my rail will be modeled as a beam, my deck will be modeled as beams, and my columns as well, if I'm modeling, it will be modeled as beams. Okay, so the main thing which will govern this analysis is the modeling of my ballast or concrete bed, whatever is this in your case. So now for our case, suppose as I told you, it is a bilinear curve for ballast as per UIC. So, and for loaded it is different, and for unloaded it is different. So, we are going to model them as multilinear links with the stiffness governing as per these curves. So, for loaded condition, I will use a different multilinear spring, and for unloaded condition, I will use a different multilinear spring. Okay, and those will be, my rail will be connected to my deck using these multilinear springs, and then the top of the deck will be connected to the bottom of the deck using a rigid link, and then below that I will model the bearings, which will be elastic links. So the stiffness of the bearings will be dependent on the type of bearing which I am providing. So suppose if I am going for an elastomeric bearing, so based on the shear rating of the elastomeric bearing, and I will arrive at the longitudinal stiffness, and I will provide same stiffness to my elastic link here. So this is how will be going to generate the model. So as I told you, there are two ways to do the analysis. But one is separate analysis, where I do separate analysis for thermal loading, traction braking, and train vertical loading, and I combine them linearly and get the stresses. And the second is complete analysis, where thermal loading, traction loading, train loading, all these are applied in a single model, and the stresses are calculated. So as I told you, separate analysis are they produce more axial force in your rail. They are conservative approach. It gives around 10 to 15-20% more results in the rail. So this being conservative, usually it is easier to perform the analysis. So usually people go for this type of for simplified separate analysis. Now to show you the difference, so this being my ballast stiffness. So as I told you, for unloaded condition, so this is my unloaded stiffness. So for unloaded condition, only thermal load will be acting. So suppose this much stiffness has been of my ballast has already been utilized. So now when my loading is coming, so if I am doing separate analysis for unloaded condition, suppose stiffness of my ballast is 25. So this 25 stiffness is already consumed by my temperature load case. But if I am now doing for live load analysis on the different model, so it will take 50. From here it will take 50. So the total stiffness here it will become 75. However, the total stiffness of my ballast is only 50, that too in loaded condition. So this increase in stiffness, so it will take the stiffness of ballast on a higher side. So this will give rise to higher stresses in my rail. So this may be a more conservative approach. However, if I apply the same loading in same model, so here it will not breach the stiffness of the ballast which I have defined. So here it is more of a realistic kind of analysis. So now let me take you to the rail structure interaction wizard, where we will see how we have to do the rail structure how we do rail structure interaction analysis there. So let me take you to the software now. So, so just to give you a brief introduction of the software if you are attending this for the first time. So this is my main menu basically. So this is designed as per the workflow of an engineer. So starting from here you can generate the full model till your boundary condition, and then you can apply your loadings. Then you can perform the analysis, get the results, and then you can do the design if required. So based on all these things, we can generate the model. So here, if you go in structure, and this is my main modeling window. This is my tree menu 1, and this is my tree menu 2, and this is my message window. So if I'm doing analysis, if any error messages are coming, so those things will be displayed here. Okay, so now I will just take you to this rail structure analysis wizard. So this is present here. This is present in structures, rail track analysis model. So if I click here, this new window will pop up. So this is my main window. So here I have to specify the layout of my bridge. So depending on, I have to select my bridge material, that is the deck and support material. Then deck information I need to provide. So what kind of deck? Suppose force span of 30. So like that I can give force span of 30 and embankment length. So this embankment length, as per if you ask me about UIC guidelines, so UIC tells to model at least 150 meter of embankment length on both the sides. Okay, so based on that, whatever type of condition you have in your bridge, we need to give the embankment length. Then the span type. So here there are different types of span. So any of the, suppose it is simply supported, then you can go if it comes 2 span continuous, 3 span continuous, or if you have 4 span, 5 span continuous. So any type of advanced spanning configuration can also be defined here in the advanced span type option. Okay. Then the second thing here which we need to specify is the rail material. So the type of rail which you are using, what is the stiffness, what is the material being used for a rail. So based on that, I will give the rail material here. Then we need to specify the number of tracks. It is 1 track or 2 track. Then the additional checks. What are the additional checks? So additional checks are nothing but the zero resistance, zero longitudinal resistance, and rail expansion joint. So as I told you earlier, so you just need to specify the position where you are providing these, and it will take into consideration analysis. Okay. Then this thing is, now here will be the section. So what is the section of your deck? So we need to specify the section of deck here. So bridge section you can specify. Then eccentricity between the rail and the slab. So this is the eccentricity. Basically, this is from the centroid of your rail to the top of your deck. So this is based on the type. So how your arrangement is. So basically, usually the arrangement is there will be your rail. Below this there will be the sleeper, and below sleeper there will be the ballast. So usually for typical railway bridges, if you see, the depth of ballast provided is 300 to 350 mm square. 300 to 350 mm, and the sleeper depth is given in IRS code. So this total eccentricity comes out to be 750 mm. Okay, so this, as per your case, you can give this eccentricity. Then coming to rail section. So in the software there are already 3 rail sections. In the database. So for our usually India UIC 60 is used. So depending on any other type of rail, either you can import it from AutoCAD, that section, and create a section here, and we can use that, or we can directly use this UIC section. So this UIC 60 section I can import from here and I can use it. Okay. So this is for section part. So similarly, all these, if you have different decks, for different span you have different deck configuration, so you can update as per your deck configuration. Okay, and another thing, define track position. So basically this gives the position of track from the centroid of your girder. So based on what is the spacing between your rails, if you are giving two rails, so that you need to give. So usually for Indian scenario, this total distance between the two rails is 6 meters, so D1, D2 will be 3 meters. Okay, so now coming to boundary. So as I told you earlier, the stiffness of ballast and concrete bed, it changes if it is loaded and if it is unloaded condition. So based on whatever, if you may be having the guidelines or you may be having the values of your ballast or concrete bed for your bridge, but if you go as per codal provisions, so IRS code tells this UD as 0.002, that is 2 mm, and the F max value for stress check, it gives us 50, and sorry, for this is as 25, and for loaded condition it goes to 50, double the stiffness. So if you have ballast bed or concrete bed, you can specify the stiffness criteria. And if you have a special type of arrangement, suppose on the embankment you have a ballast bed, but on the if you have on the embankment you have ballast bed, but on the bridge you have a concrete bed. So based on that arrangement, you can give the type of, suppose from start 0 to 100 you have embankment, and there you have concrete bed, sorry, ballast bed. So you can give that, and from 100 to 200 is your bridge. So from 100 to 200, you give concrete bed. Similarly, whatever type of arrangement you have, you need to specify it here. Okay. So now coming to boundary condition. So there are two ways to do this. So either I can go with spring type. So in spring type, it will not model your substructure, but if I go for bearing type, it will model substructure as well. So in spring type, whatever stiffness you are getting for the substructure, you need to give the same stiffness to the spring type. But for embankment, we need to, for bearing type, we need to give the stiffness of the spring. Whatever stiffness of your bearing you are arriving at, the same bearing stiffness need to be updated for your these elastic links, which will be there. And rest of the arrangement from deck to rail, I have already explained it to you. They are connected via multilinear links, where the stiffness is defined as per loaded and unloaded condition, which we have defined here. Okay, so this being said, now moving on. Now coming to loading. Okay, so first for deck and rail temperature loading. So this various codal provisions will have various guidelines, but for if you talk about UIC, for deck it tells to do 35 degrees centigrade, and for rail, if it is coming in the non expansion zone, so in that case we don't need to apply any temperature load to the rail. And for for temperature case, we don't need to provide any puzzle. Now coming to this moving load. So basically now this load, if you have two tracks, so train moving keep left, if we select keep left, so from the train will start from left and move to right, and similarly the opposite train will move in the opposite direction. Okay, the other track will move in opposite direction. Now here we need to give the load type, what type of load we are giving, and the start point, and till where this load is coming. So suppose till 100, my vertical load is 171. This vertical load value I have arrived from, this is vertical. This vertical load value I have arrived from IRS code guidelines in annexure 26, where they have given the EUDL load for vertical braking and traction for 30 meter span. Okay, so like this, I need to, so the load value, sorry, I have to give the load value here. Start point, suppose 0, 200. So that thing I have to update here. So based on that, it will take the value. Similarly, for braking and traction, I need to give. Okay, so same way for now, if I want to create the increments, so those increments I will create. So this is the static load case which you have defined. Now we have to give the convert this into a static. Now we have to give moving load data. So based on your span configuration, you can give your increment. Suppose mine is a 30 meter span. Okay, and I have a 3 span bridge. So I will give 3 increments and I will give 30 and minus 30 here. Okay, so basically we are converting the moving load analysis into static, moving dynamic analysis into static moving analysis. So basically it will be creating different models at different loadings. So one model will be created with this original condition, second model will be created with an increment of 30 meter, and similarly like this 4 models will be created. Okay, so this is as for the loading. So coming to element length, so usually whatever is can we usually go for 1 meter and element length. Now stress check, as I told you, simplified, separate and complete. So if we go with simplified separate, we can select what is the output we are expecting, and based on that the report will be generated. Okay, so now let me take you back to the presentation now once. So this is how the loading and wizard will work. So once I will just show you one model which we will create, and based on that we will see the stresses and reports. Okay, so this thing we have already discussed. Okay, so the section which we'll be using here will be ESC box girder bridge section. So this is the section we are using. So these are the dimensions which we'll be using. Okay, so now what we will do, we will create one model for ourselves. Sorry. So this is the base model which we'll be using to create our model. Sorry about that. Okay, so this is the base model which we'll be using. So these are the section, mid section which we have defined. So you can see this is my PSC box girder section. Okay, so I will just open the Real Structure Interaction Analysis wizard. So here we have this option. I've already created this wizard file here. So we'll be using this for our bridge. So you can save at any point of time, you can save whatever data you have entered here. I can save that as a wizard file. So this is very easy, a very good thing actually. So you can use this once we have saved the data, then we can call it at any point of time and we can create the model for ourselves. Okay, so now this we are doing for a 3-span, 30-meter span, and embankment length I have kept as 100 meters. So ideally I should keep it as 150 meters, but for analysis time will be very high. So for that I have kept it as 100, and I have taken simply supported span. Rail material I have kept as FE540. Sorry. And the bridge section as already defined, and the eccentricity I have kept it as 750 mm. And this I will add UIC section. So I'll be using UIC section. And the track position I have kept it as 3 meters apart from the center line. So if you want to see how my section will be going to look. So this is my bridge. This is the 750 mm space. Sorry, 750 mm eccentricity and the rails. Okay, so this is the bridge. Similarly, I have created the ballast stiffness. So 2 mm displacement, I will get stiffness of 25 for unloaded condition and 50 for loaded condition. And bearing I have taken as 13,000 kN longitudinal stiffness. Okay, elastic link based on your depth of bearing, you can take that. And modeling of substructure also I am doing in this. So the pier section I am taking it as 1x1, and pier material is M40 and pier height is 10 meters. Okay, and bottom of the pier I will keep it as fixed. Okay, and now coming to loading, for deck temperature I am taking it as 335 degrees centigrade for deck, and I am considering my bridge to be in non-expansion zone, which is the most critical case. So for that I don't need to apply real temperature. Now coming to loading, for vertical I have 171 kilonewton, and from 0 to 100, which is my embankment length, 0 being the starting point of my embankment length and 100 being the end point. And this braking also I will apply till embankment first, and vertical on one track it will be braking, on the other track it will be acceleration, and because that case only will generate maximum impact on my bridge, so that's why I'm checking for that case itself. Okay, so based on these values I have arrived from IRS codal guidelines, and my span being 30 meters and 3 span, so I have given 3 increments of my loading. Okay, and the element length I have kept as 1 meter, and I'm going for simplified separate analysis. Okay, so once I will press OK, it will generate the model for us. So now you can see the model has been generated by the software for Real Structure Interaction Analysis. So now you can see here, so this is my deck, and these are my columns, and this is my rails. So if you see so you can see, so if you notice here, actually the software creates an equivalent rail here. So instead of modeling 2 rails, what it does, it takes the equivalent rail, and the properties of the single rail is equivalent of 2 rails. So similarly on the other side, so this is a two rails are there, one up track and one down track. So both are modeled as equivalent. Okay, and this is my 750 eccentricity. So if you want to see the boundary properties, so I'll just activate all the boundaries here. So now you can see, so these boundaries has been, so this is nothing but my ballast, these elastic links which you see here, multilinear elastic links. And this is a rigid elastic link which is connecting from the top to the bottom of my girder. And what you see here is link simulating my bearing. Okay, if you see the multi forcing function, you can see here. So 0 to 12.5. So basically, this is the end spring. So the stiffness of my multilinear elastic link is 25 kilonewton per meter square. So influence area for this spring will be 0.5. So that's why it is created 12.5 spring. So if you see here, this is the 25 unloaded spring. So this is for temperature loading itself. So temperature loading is unloaded condition. And you can see the piers are also created. So this is for temperature case. So if you want to see the loading, you can see the deck loading has been applied of 35 degrees centigrade. Okay. So this is for temperature. Similarly, if you see here, the software will create various loadings. So basically based on, I have given 3 increments of moving load, 30 meters spacing. So based on that, it has created my 3 moving load spacings. 3 models for each braking, 3 models for vertical, and 1 model for temperature. So if you want me to open one of the other loading models. Just a moment. Sorry. So this is the third moving load condition. So here now you see there are 4 multilinear springs. So one is for loaded condition, which is 50, and one is for unloaded condition, which is 25. And coming to load, let me display that. So these are the braking load, braking and traction load. So on one track I have applied braking load, on other track it is traction load. So this loading is the third moving load. If you see, this is the third moving load. So basically we started with 0 with here, from here. So first increment gave me at 30 meters, second at 60, and third at 90. So this is the third increment. So based on this, so this model has been created. Now we need to analyze and generate the report. Okay. So for that I will go to analysis. Sorry, I need to go to structure and radio track analysis report. So once we do that, so it will consider all these models which we have created, and it will create an envelope. It will extract results from all these 9-10 models, and it will extract the results and make an envelope case for us to get the maximum, minimum, all the required stresses in the real governing stresses and the serviceability criteria. So these values I can change as per my requirement. So as per IRS, compressive stress is 60 MPa and tensile stress is 75 MPa. Permissible limits are same. So once I press OK, so now it will start analyzing all the models and it will start extracting the results. So this process will take a little bit time. So I have already generated the report for this case. So let me show you that. So this is the report which was generated for this case. So now you can see this is my temperature graph. So if you want to see the stresses coming due to rail structure interaction temperature case, it is coming out to be 11.54 MPa. Okay, so this is the stresses which are coming due to temperature. If you want to see due to braking and traction, I am getting maximum of 46 tensile stress and compressive 50.49 MPa. And due to vertical bending, I am getting 10 and 17 due to tension and compression. So due to all temperature, braking, traction and vertical, the maximum tensile stress I am getting as 57 MPa and maximum compressive stress and rail I am getting as 50 MPa. So it is well within the limit. So if you compare it as per IRS case, it is 75. So this is less than 75 and this is 60. So this is also less than 60. Okay. Similarly, if you see the absolute displacement, now absolute horizontal displacement of deck due to braking and traction, this is exceeding the limit of 5 mm. So here we need to check. So how we need to change some of the parameters, or we need to change the span configuration, or we need to reduce this value. And similarly for relative horizontal deformation of rail 1 due to braking and traction, it is also exceeding to 4.9. Okay, so and the deck end rotation, it is less than 8 mm. So this is in control. Okay, so these are the rest of the sheets are individual stress extraction. So this thing will be automatically generated for simplified separate analysis by the software. Okay, so it is a very tedious task to extract results from all the models and compile them and get an envelope. So that part has been made easy by the software, and this type of summary report is generated for you. So you can see the stresses for each and every moving load. So 4 load cases for each case, so you can see that. Okay. So this is how the rail structure interaction analysis is done in the software. So I will take you back to the presentation notes, and you will see some of the case studies which we have done. Okay, so longitudinal resistance of track versus the longitudinal displacement of rail. Okay, so now you know that the stiffness of my ballast will be less than that of the stiffness of my frozen ballast or concrete bed. So due to this change in stiffness of my ballast or concrete bed, the stresses in my bridge may also, the stresses in my rail may also change. So if you see this comparison, so if you see here, so for unloaded condition, so this being for my ballast and this being for my concrete bed. So you can see here for ballast, the stresses are comparatively less in my rail. As I told you, the stiffness of ballast is less than that of stiffness of my deck. So the less the stiffness, the less force will be generated in the rail. So you can see here around 30% less stress in ballast track than the concrete track under same conditions. So one thing to learn from here is stresses will be more for concrete bed than for ballast, but the displacement, the serviceability criteria will be less governing as compared to ballast bed. Second is the zero longitudinal resistant fasteners. So by doing that, we can reduce 29% of the axial stress in my rail. So that is, if we go for that, that can be done. Now, expansion length. So basically, depending on your span configuration which you are giving, based on that, your expansion length will also change. So based on expansion length, the stresses in your bridges will also change. Okay, so this is for temperature stress. So based on all these criteria, so as you can see, the minimum you are getting is for simply supported kind of arrangement. Okay, and maximum which we are getting for is this when the span is two span continuous. Okay, so span length. Uh, the other factors which are affecting the axial force in the bridge is the span length, as we know. The more longer the span, the more bending, the more stresses will be generated in my rail. Then bending stiffness of the deck, as I already explained it to you. This we have already covered. That the more the deck will bend, the more stresses it will give rise in more stresses in my rail. So the more stiffer my deck, the less in my stresses in my rail. Then the support stiffness. So you might be knowing this. My support stiffness comprises of bending of pier, rotation of foundation, and displacement of foundation. If I am able to curve this, if I am able to increase this stiffness, the stresses in my rail will also reduce. Okay, and the effects of layout of the span configuration, as I've already discussed. So based on the fixed free arrangement and how I am keeping my fixed arrangement where. So based on that, the stresses will also change. Okay, and the span composition. If I am keeping my larger span so if you see the span configuration here, sorry. So larger the span on the free end, more the stresses, and larger the span towards the fixed support, the stresses will be less. So this is another thing which we can consider. So yeah, so this was for today's webinar on rail structure interaction. I tried to cover as much as possible. So if you have any questions at this point of time, kindly let me know so that I will answer a few of them. Okay. So how to calculate the braking load? So to calculate the braking load, as I have told you, so based on the different code, it will depends on the what type of loading you are applying on the bridge. So if you are going for suppose IRS, I can show you for IRS loading. So let me just yeah. So let me open that IRS code just in a moment. So if you see, this is the bridge rules as per IRS bridge rules. So if you see, let me just open that. So suppose for this loading is for 25 ton loading. So based on that, based on your span length, so whatever is your span length, this is the converted equivalent EUDL loading. So based on your span length, you will get your total whatever load is coming on the span. If you divide it by your span length, you will get equivalent loading. So you can apply this, and you can uh, you can do the analysis. Then how to modify the model for curved alignment. So as of now, rail structure interaction module, the wizard which we have here, we don't have curved alignment as of now. So that curvature we need to create it manually. So to create that manually, we need to modify the node points, and we need to change the whatever links we have provided. We need to change the beta angles for those links. So, what about the derailment roads on the concrete bed? So, basically, this rail structure interaction is basically a check. So, once you have designed the bridge, after that we are checking it if my bridge is passing for rail structure interaction or not. So, these derailment loads and curvature loads and all the other type of loads we need to consider during design. So, this is post-design kind of a check thing. So we take an allowance of, so whatever design forces we are getting, so we take an allowance of 5 to 10%, and we design the bridge, and then we check it for rail structure interaction. But because you can see here, we need everything about the bridge. We need the pier sections, we need the deck arrangement, and everything which has been finalized, and on that we are doing this rail structure interaction check. So these derailment loads, these need to be considered during my design time. Yeah. Why rail track is modeled even outside the bridge deck? Rail track is not outside the bridge deck, if you can see here. It is inside my bridge deck. So this is the equivalent rail. So one rail will be coming here, other rail will be coming here. One rail will be coming here, other rail will be coming here. So, the boundary condition for my rail in the embankment. So if you see here, this is my embankment part. So the bottom point of my embankment is fixed. This is completely fixed, and the rail and my embankment, it is connected with the same multilinear elastic links. So this is representing my ballast. So whatever ballast is available. So depending on it is loaded or unloaded, it will have that multilinear link stiffness of loaded or unloaded. Okay, so as of now, I think I've answered all the questions. Uh, for, for slab, for slab track, for slab track on viaduct, example in metros, CWR is carried out throughout. However, largest rail stresses is generally found at longest span. Yeah, that is true. For longest span, we'll get more rail stresses. Should string be modeled with same pre-stiffness at each end? In that case, I'm not sure what do you mean by string. Can you elaborate on that rail string? So basically, yeah, what you are saying is true. For the larger the span, the more stresses we will get in our rail, as because bending will be more, the structure will become more flexible. So yeah, but I don't think we need to model it with pre stiffness at each end. So whatever, first we will take it as a rest condition, and whatever loads are coming, so whatever stresses it is coming because of that, we need to consider that. Mm. How to apply rail braking force? So if you see here, I have applied rail braking force in this case. Yeah. So if you see, the software will automatically, the whatever loadings we have defined, basically based on that, it will automatically create the loadings. So if you see here, this is a braking load which we have applied here. So if let me open that file again which we have created. Uh, so if you see, for loading, so here I have created a braking load of 22.05 from 0 to 105. So you can see here this is the 22.05 braking load which is applied on the track, and similarly the acceleration load which are defined as 32.65, the same acceleration load is defined here. So whatever loading which you specify in the rail track analysis wizard, so that stiffness will be that force will be applied on the model, and the four models, as I showed you, four different models are created based on the increments which we have created, and these loads will keep on moving with this increment. Okay, I hope this is clear. Okay, and what embankment is not. So rail fracture load. So as I told you, this is the interaction effect that we are checking. So rail fracture load, I am not aware of it actually. So if you can send me the details of how it is going to act and when, at what condition it is going to act, then I can show you how to apply it in the model. So the basic idea, as I already told you, this is a design check which we are doing after once I have completed my design. So I'm going to check my structure if it is passing for rail structure interaction or not. So rail fracture load, yeah, I'm not sure of that. Kindly let me know in detail so I can help you more on that. What boundary condition I have to give to rail at the end in the longitudinal direction. So basically, at the end, what we have done is the main purpose of modeling the embankment. If you read the UIC code, the main purpose why we are modeling this embankment is because we don't know the end condition of my rail here. At the end of the bridge, what is the end condition? Basically, my rail is continuous, but the support system for my rail is changing. So if you see here, it is on ground here, and here it is on bridge. So here we don't know what boundary condition we need to give. That's why we are modeling an embankment of 150 meters. So at the end of the embankment, basically I will keep it as free only. So because I am concerned about my stresses, whatever stresses I am getting in this part of my bridge. So I am not concerned about boundary what I am giving here. And for this boundary, the reason I am making this embankment. So the load increment, basically what so this is my three-span bridge. So the first, so I am concerned about my stresses on my rail in this bridge location, because at the embankment it is resting on ground, so the stresses will be predominantly compressive. But here on the bridge, as my deck is not completely rigid, it is flexible, it will bend, so it will induce stresses in my rail. So I am concerned about the stresses, what stresses are generated in my rail on the bridge location. So I can't do a normal moving load analysis as this is a nonlinear analysis. So what I go for is I will create loading conditions. So first load position, what I will do, I will start from this embankment, I will load it till the beginning of my abutment. So this is that load condition which I have defined here. So if you see here 0, this is my 0 start point, and the end point is 100 here. So this is the 100-meter embankment. So here I have loaded this, and I have given increments of 30 meters. So why I have selected 30 meters is I have that is the span length of my bridge. So this is 30 meter span, 30 meter and 30 meter. So as I know, my predominant forces will be coming at my support locations. So abutment piers, I will get predominant loads at this location. So these will be my governing conditions. So that's why I have given my moving load increment of 30 meters. So here 30 meter, 30 meter, 30 meter. So for that I have created 3 increments, and that's how we will define the increments for the bridge. Okay, so I hope I have answered most of the questions. So still, if there are any more questions, I will be answering them via email. So this webinar will be uploaded on YouTube. So this link will be shared to you. So for future reference. So thank you for being a part of this webinar. Hope you find it helpful. Hope thank you for listening to me so patiently. I will try to answer all of your questions. I will compile all the questions. I will answer them. So don't worry about that. And yeah, so I will be ending this webinar now. So thank you very much for attending and hope to see you soon. So this is an ongoing lecture series. So this was the fourth lecture of that lecture series, Midas lecture series. So there are four more videos, four more webinars which will be held shortly. So keep attending them and hope you find them helpful. So thank you.